Okay, so now we're going to look at NMR. And the first NMR we're going to look at is Proton Nmr. So I'm going to write that up here in this corner. Proton Nmr is actually the name for hydrogen isotope 1. We're going to talk about the other isotope of hydrogen in a minute, but isotope 1 of hydrogen on our planet is over 99% of the hydrogen isotopes. So the majority of hydrogen is isotope 1. And it's kind of a funny story because back before they were developing this, a physical chemist was trying to prove that the magnetic signature of all the nuclei, which is inside of hydrogens, were all identical. And he built his first magnet, and he ran his first sample, and I think he tested ethanol, and he ended up with 3 different signals just from one compound, and it disproved his entire hypothesis. Since then, luckily he had an organic chemistry professor as a friend. He says, "You have a machine that can distinguish the different hydrogens?" And he said, "Yes." And from that, a whole world of NMR has developed. Now, in the world of NMR, there's 2 parts you must understand. The first part you want to kind of know intuitively is called the relative shifting. And that is, where do the hydrogens normally place on a given set of frequencies, and then how do functional groups cause that signal to move to a different position on the frequencies. Alright, so we're going to start with shifts first, and I'm going to draw a fairly large line here and try to divide it up. I highly recommend you guys do the same. So we're going to start at 0, and we're going to go to 1, and then got to keep it about the same. 2, 3, 4, 5, 6, 7, 8, 9, 10, and there's actually some peaks that go higher than 10. So let me put in all the numbers. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So the first thing is just to know what a normal carbon looks like. And the normal carbons are usually divided into the categories methyls, primary, secondary, and tertiary. And if they're on a chain, then you're only going to have primary, secondary, and tertiary. Methyls are when they stand all alone. And so the primary carbons, let's divide up this region. So 0.9, 0.8, 0.7. The normal hydrogen that's on the primary carbon usually creates a signal right around 0.7. If it's on a secondary carbon, it usually right around 0.8. If it's on a tertiary carbon, it'll move up to about 0.9. So these are very close positions for peaks to occur, and we haven't even gone to the splitting patterns. If the signal is moved to anywhere else on this spectrum, then it's not a normal hydrocarbon or a normal alkene. So your normal alkanes all have signals that just show up somewhere in here, and if they overlap on top of each other, it's hard to distinguish one from the other. Okay, so the first effect that we studied in shifting these was the effect of highly electronegative atoms. And the most common one, of course, is oxygen. So what happens is a lot of your textbooks will have an electronegative atom attached to carbon. What happened to that hydrogen? X, the electronegative atom is X. We're going to start with oxygen. That's the most common one. All the halogens, fluorine, chlorine, bromine, and iodine, have an electronegative atom effect. And I'm going to also include sulfur. The one that the book includes is nitrogen, and we're going to move nitrogen somewhere else. Nitrogen should not be included in with this grouping. What happens now is this hydrogen signal, instead of being down here between 0.7 and 0.9, is now between 3.1 and 3.4. So they tend to move to 3.1 up to about 3.5. Their signal has been shifted from here to here. Okay, let's throw nitrogen into the works. If nitrogen was the electronegative atom that is on the carbon that is attached to the hydrogen, then that usually this signal shows up right about 2.8. So I'm going to write 2.8 is the normal shift for that signal, and they all tend to pile up right around 2.8. You rarely ever make it above 3. Whereas oxygens and the halogens, they always go above 3. Okay. So that was our first study, was what's the effect of an electronegative atom on the position of these signals. Okay. The next one was what's the effect of pi clouds. Well, it ends up being that a pi cloud actually creates a magnetic field of its own, and that magnetic field interferes with the magnetic signature of the hydrogen, and that causes, if we just have a simple carbon-carbon double bond, for example, that hydrogen's position will move to 4.5, and sometimes, if there's other things, because shifting can be cumulative, up above 6. But normally, I'm going to put this one really dark, it's right around 4.5 to 5. If it goes above 5, that usually means there might be something else attached, or another pi bond in conjugation, or there's an oxygen or nitrogen nearby, because you can have what's called a second effect, a next door effect. But this is the direct effect of this pi bond. This pi bond caused this signal to shift down to at least 4.5, if not higher. Okay, so while we're doing pi bonds, the next area, which is a large, like I said, a large portion of this semester, is the aromatics. When you have a benzene ring, you have these hydrogens that are stuck on a conjugated pi system. The normal benzene ring and normal alkane benzenes like toluene and cumene, their hydrogen signals for all the hydrogens that are on the benzene ring usually approximate 7.1. So really close to 7.1. We're going to write 7.1 approximately. Okay. These signals will this hydrogen will be right about here. Okay. Here's the interesting thing about benzene rings. And you're going to have, as I said, a whole chapter just on the effects. When you add something ortho or para to a hydrogen, that we'll call it substance X, and we're going to look at the ortho and para effects, and we'll look at it in great detail when we go to that chapter. But a substituent that's attached to a benzene ring, like here's para and this would be ortho, can cause, depending on the substituent, this signal to either move this way or to move up this way. And the rule was pretty simple. If X was a strong electron donating group, like an oxygen or a nitrogen that was an amine or an ether, the signal always moved up to below 7. Like 6.8, 6.9. So strong electron donating groups always shift the hydrogens that are ortho and para to the donating group to this side. And I'll show you some examples a little later. Okay, conversely, the opposite of an electron donating group is a strong electron withdrawing group. Now, electron withdrawing groups actually have moderate and strong ones, and they have the opposite effect. So electron withdrawing group, for example, a strong one would be a nitro group. A nitro group would move this signal way over here, somewhere 8.5, maybe 9. A moderate electron withdrawing group might just move it up to just below 8, like a carbonyl. There's a lot of different types of electron withdrawing groups. So electron withdrawing groups move this hydrogen. Again, it has to be ortho or para. I should put a line there. It has to be ortho or para to this hydrogen. They shift. And so what's interesting is if you have one of these substituent on, the ortho and para hydrogens move, but the meta one, they stay more or less where they were meant to be, which is around 7.1. And so there are clues if these move as to what the structure is based on the position of the aromatic hydrogens. Okay. Now, the next functional group that you need to know is the combination of two effects at the same time. And that is the combination of a pi bond to an oxygen with a hydrogen on it. That functional group, you should recognize. Whoops, man, this camera's really our table's rocking. This is typical of the aldehyde hydrogen, or a special carbonyl that has a hydrogen stuck on the side. And just to review, in case the other video is too blurry to look at, the normal position of alkane hydrogens is always right below 1, 0.9 to 0.7. Electronegative effects is around 3 point something, unless it's nitrogen, then it's around 2.8. The pi bond effects start at 4.5 and go up to about 6.5. The aromatics are usually around 7.1, unless they're strong electron withdrawing or donating groups, and they shift to this side if they're donating, usually less than 7. Withdrawing groups always shift towards 8 or even go up. Now we're going to combine an electronegative atom with a pi bond. This effect moves these hydrogens to the 9.5 zone, approximately 9.5. Now these positions are often referred to as they have this little delta, 9.5 approximately. Okay. Now, that takes care of a lot of your CHs, except for a few that you will always run into. And that is the effect 2 away of the strongest strongest hydrogen shifting groups. So the carbonyl and the aromatic rings have such a strong magnetic shielding effect that they will actually affect hydrogens of one carbon over. We call it the next door effect. So that next door effect actually occurs usually around 2.1, 2.2. So I'm going to put a little line here. So we're approximately at delta 2.1, and that would be if you're next door to a carbonyl on a carbon that has a hydrogen. Okay. So you're not on the carbonyl directly, you're next door. These hydrogens feel somewhat of his effect and become shifted from here up to 2.1. The same thing happens if you're next door to a benzene ring. So the shortcut symbol for a benzene ring is this null sign. So if you're a carbon on a hydrogen and that carbon is touching a benzene ring, that will also be shifted, these hydrogens, from here up to 2.1 in their relatively shift position. Okay. So that covers almost every type of carbon hydrogen you see, except for one, the really rare one. What's the rare one? Well, that's that sp1 carbon-carbon triple bond. The sp1 hydrogens are unique in that they don't see the magnetic field. They have what's called too much S character. There's a lot of reasons for it, but generally speaking, and it's not perfect, if I'm going to put this one underneath, if you happen to have a triple bonded carbon and at the end of the chain it has a hydrogen, So again, this has to be a terminal alkyne. This hydrogen does not shift way up here to 4.5. It only has about half the shift, which is usually around 2.5. It can range though anywhere between 2.1 and 2.8, but I'm going to put it at approximately 2.5. Again, it will depend on what else is on the ring. Okay, so that took care of, I think, all the hydrogens on carbon. What are the other hydrogens you see? Well, those are hydrogens on oxygen and nitrogen, the OHs and the NHs. So what happens with these is they actually range. So let's do simple amines and simple alcohols. Simple amines and simple alcohols, the OHs can range anywhere, and these are OHs or NHs, anywhere between 1 to 5. They have some unique characteristics. They tend to never have splitting patterns. They tend to always be broad singlets. Or in other words, they look like a lump. Oftentimes they're around 2 to 3 or 3 to 4, but they actually move based on what solvent was used to run the spectrum inside of the NMR. So using one solvent, an OH might be here. You switch solvents, the OH will shift over there, or shift over here. They can move around. But when we say a broad singlet, instead of being a spiky peak like this, I'm going to put a little lump. It'll just be a lump. Oftentimes it'll be a lump. There's something else important about the OH, and that's the other isotope of hydrogen. So let's talk about that right now. Hydrogen 2. Hydrogen 2 exists on our planet at 0.8% of the time. Which you would say, well, that's less than 1%, but it's a significant amount that we can actually collect it and make pure hydrogen 2 samples if we want. Hydrogen is the one element that all of its isotopes receive names. So the name for hydrogen 2 is deuterium. And it's given its own symbol, which is the uppercase D. And I'm going to throw this other one in just for fun, but it's not part of NMR, and that's the other isotope of hydrogen. On this planet, hydrogen only has 3 isotopes. Hydrogen 1, which is the majority, hydrogen 2, and hydrogen 3 is the one that's a trace amount on this planet. He is called tritium. And like deuterium, he's given his own symbol, which is the uppercase D, T. Okay, what's interesting about deuterium is deuterium has 0 magnetic presence. So if you were to take a compound and swap out all the hydrogens for deuterium, you would see nothing. Likewise, if you take a compound that has either an OH or an NH or other highly acidic hydrogens, an instantaneous exchange happens with acidic hydrogens in deuterated water. So I'm going to use ethyl alcohol as a simple example. Okay, and so if we did ethyl alcohol, and ethyl alcohol normally has hydrogen 1, so ethyl alcohol would have hydrogens on this carbon, that would be one signal. Then it'll have hydrogens on this carbon, that would be a different signal. And then it would have the hydrogen for the OH, which would be a third signal. So technically, ethanol will have 3 different signals across here based on the hydrogen's environment. If you were to add deuterated water, so let's make deuterated water brown. So that's hydrogen 2 with hydrogen 2, where they enriched the deuterium on water. And another way of writing deuterated water is D2O. Basically, it's just the other isotope of water. What happens is any hydrogens that hydrogen bond instantaneously start swapping places. The speed of acid-base reactions, we drill this over and over. What happens first in all reaction? The answer is acid-base. They happen nearly at the speed of electricity, especially in solutions. And in that time, the hydrogens that were on the alcohol, if you add enough deuterated water, will all switch to deuteriums. When that happens, this guy's signal that used to exist disappears. It goes away. So in your NMR problems, particularly at the end of the chapter problems, when they say the signal at delta such and such disappeared in deuterated water, or D2O, that means it was hydrogen bonding. Okay, so I'm going to just write that note here. The signal disappears. And that's an important clue, especially in your homework problems and your quiz and exam problems, is, oh, that was an OH or that was an NH. But OHs always swap instantly. Okay, so while we're talking about OHs, let's go back to where do they usually show up. So general alcohols and amines are usually between 5 to 1, somewhere single. Sometimes, though, OHs will shift higher. For example, the phenol. We have one chapter in my course where we just study phenols. Phenols are more acidic hydrogens than normal alcohols. Consequently, these guys tend to show up somewhere between 5 and 9. It's hard to predict where a phenol shows up, but it's usually not down here. So I'm going to say delta 5 to 9. I've often seen phenols show up around 6.5, sometimes up at 9. Again, they can move around. It depends what else is on the benzene ring as to where the phenol OH will show up. And that brings me to the most acidic of all oxygen-hydrogen bonds, which is the carboxylic acids. Carboxylic acids, is this my brown? Carboxylic acid, that OH is super shifted if you think about it. It's next to the carbonyl, it's on the OH, it's actually hydrogen bonding between the two, and generally these guys can show up anywhere from delta 10 up to 15. Again, depending on what else is on the next to the carbon. And they will also be broad singlets. They will also disappear completely when you add deuterium. And so, again, the deuterium test is for OHs and NHs. Do they swap instantly? There are a few other acidic functional groups that will swap deuteriums, but usually not as fast as the OH and the NH. Okay, so the first thing, as I said, that we need to master is the relative position of where these signals show up. The second thing is what's called the next door effect, the magnetic effect of splitting neighbors. What happens is, and I'll use ethanol as my first example, these guys have their magnetic position. And since there are 3 hydrogens on the same carbon, they'll all have identically the same type of position. But next door, these hydrogens have a different position because they're next to the oxygen, and so their signal will probably be somewhere in the 3 to 3.5 range, and they will have a different magnetic signature. And when magnetic signatures are next to magnetic signatures, they split each other based on Pascal's pyramid. I'm going to give you Pascal's pyramid really fast. It was something I had to do in grade school. This was way back before calculators were invented. But if you take a signal and it has nothing to split it, it stays as a single peak. And so chemists like to call it a singlet. If it has one next door neighbor, then the signal gets split in half into two peaks, and chemists like to call the two peaks a doublet. Okay. What happens next, if there happen to be, for this next door to the singlet, two neighbors, then it gets split again. So the first split, then the second split, splits this peak in half, plus it splits this peak in half. And because the middle part overlaps, you obtain this ratio that's called a 1 to 2 to 1 ratio. This 1 to 2 to 1 splitting pattern is typical of what we like to call a triplet. Okay, now let's continue and do one more split, and then I will stop drawing. If there was, so this was 0 neighbors, I'm going to put 0. Then there was 1 neighbor, then there was 2 neighbors. If you had 3 neighbors, these would be split again. And so this signal will be split again in half. This one will be split in half. This one will be split in half. That'll add just a little bit more. And you end up with this pattern that has a ratio of 1 to 3 to 3 to 1. This ratio is called the quartet. Okay. Now, if you took Pascal's pyramid, which I'm going to write right next to it, I learned this way before I learned chemistry. If you start with the number 1, and then you branch and you add whatever is on the side, there's 0 on the side. So this is the number 1. You add here and you divide this guy, and he becomes 0 plus 1 is 1. 0 plus 1 is 1. And so on a doublet, you usually have a 1-to-1 ratio. Now if you take it and you branch it again, 0 plus 1 this way is 1. 1 plus 1 is 2. 1 plus 0 is 1. And you can keep growing. 1 plus 0 is still 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. And we'll go a couple more. I'm just going to keep branching. I'll let you put the lines. 1 and 3 is 4. 3 and 3 is 6. 3 and 1 is 4. 1 and 0 is 1. This is called the quintet, by the way. That's if you have 4 neighbors. So quartet is 3 neighbors. And we'll go a couple more. Actually, I like to go all the way up to 9 neighbors. 8 neighbors is usually the most you see. So 1, 4, we'll keep going. 1 plus 0 is still 1. 5, 10, 10, 5, 1. So this has 6 peaks. This is a hextet. Go to 7, 1, 6, 15, to 20, to 15, to 6, to 1. We now have 7 peaks, so that's a heptet. And we'll go to the octet. 1 to 7 to 21 to 35 to 35 to 21 to 7 to 1 ratio. Okay, and you can see as Pascal's pyramid grows, this is what the splitting signals look like. It's called the next door or the neighbor effect. Okay, so these are 1s, by the way. Sorry, my 1s do not look the best. Okay, what does that have to do? Because the splitting pattern is the second part you want to know. Well, depending on how many times the signal was split, tells you how many hydrogens were next door that were splitting it. And this is first order splitting right here. I might talk about second order in just a second. So what I'm going to do first is talk about ethanol. And then I'm going to do a whole series of compounds with the exact same empirical formula, but completely different molecular formulas. So if we look at ethanol, and the first thing in the homework, ethanol is a CH3 attached to a CH2 attached to an OH. Okay, now that's one way to draw it. Another way is I like to imagine that each carbon is a house, and living within that house, this one has 3 hydrogens. That's how many kids live in there. This house is next door to a house that has living in it 2 hydrogens. And then alcohols don't split, generally speaking, unless you have super powerful magnets. And so I just like to put the OH coming off as like a TV antenna. Of course, you will have to be older to remember the days of TV antennas. But this house representation will help me do the splitting pattern. So to say that differently, if I looked at this group of hydrogens, how many neighbors do they have? Well, they have 2 hydrogens that live next door. So that means their signal is going to be split twice. They'll be split into a triplet. Conversely, these guys that live in this house, how many neighbors do they have? Well, they see 3 hydrogens next door. So that means their signal will be split 1, 2, 3. It will be split into a quartet. So the splitting patterns will often tell us how many hydrogens are next door or who is next door to whom. Okay, so now that I have that, let's now take this concept and put it together and actually learn how to draw spectrums. And in the same time, hopefully learn how to read spectrums. So I'm going to draw a portion of the NMR spectrum that I drew before, because I'm not going to need the whole thing at this moment. And we'll go up to 5. Okay, so let's look at either one of these drawings. And I'm going to start with this one. And one of the things I like students to do is learn to label their different hydrogens. So we'll call this one hydrogens A. Just put a little circle there. These ones hydrogens B. And these ones hydrogen C. Okay, and on almost all tests and homeworks, I ask the students to do the same thing. So I'm going to actually start with B, because B is touching the oxygen. See, it's the house with the oxygen on it. That means those hydrogens are going to be shifted by that oxygen. And if you guys remember, that shift is somewhere up in the 3 zone. So the second thing I'm going to do with B is I'm going to say, okay, how many next door neighbors did he have? Well, he has 1, 2, 3. 3 neighbors means, if we remember the pyramid, he's going to be split into a quartet. So what does a quartet look like? Well, it looks like 4 peaks with a ratio of 1 to 3 to 3 to 1. If I were to draw that, then somewhere, let's see, he's primary. I'm going to put him about 3.2, maybe 3.3. He has 1 little peak. Then he has one that's 3 times bigger, and then it has that one. So a 1 to 3 to 3 to 1. This is what a quartet looks like, and that would be what B would look like. Okay, now I'll do A. A is a methyl. If you remember, methyls were 0.7. He's not touching the oxygen, so he's not going to be shifted way up here. He's 1 away, which means he gets a little bit of effect, but alcohol effects were not as big as aromatics. So he's not going to move up to 2.1 because there's definitely not a carbonyl or benzene ring right there. So from 0.7, yeah, let's move him to 0.9. Okay, we'll just say somewhere here. And this is close enough. If you put him right on 1, I'd give you full credit for that. So next question, how many neighbors does he have? Oh, he has 2 neighbors. When you have 2 neighbors, your signal is split twice. Remember the thing? So 1, 2, it should look like a triplet. That means a 1 to 2 to 1 ratio. So I'm going to draw a triplet for A right here. 1 to 2 to 1. I'm going to draw a little circle for A. So A signal will be shifted here, which isn't much of a shift, but because of the neighbors, he's split into a triplet because he had 2 neighbors next door. Okay, so that leaves C. And if you remember what I said about alcohols, they can float. So when you're drawing an NMR spectrum, find an empty spot that you haven't put anything, put a lump, and call it C. And I would be perfectly happy with a drawing that looks like that, because if you put it here or here or here, as long as you labeled it as a broad singlet, I'm happy with that. Some people will like it to be a smaller lump, but that's fine. Okay. Now, the second thing about NMR that happens in almost all your homework problems is called an integration curves. What happens is, because hydrogen 1 is so predominant in nature, the amount of area underneath the curve is exactly proportional to the number of hydrogens that they represent. Okay, so we have a computer program that integrates the area under the curve. They're called integration bars, and so sometimes you'll see them just as a simple curve like this. It looks like an integration. And since this one was worth 1 hydrogen, this guy's integration of his zone should be twice as big. Because, as I said, wait a minute, this is that one. It should be 3 times as big. Take off 1 point. I just lost a point. It should be 3 times as big. Because if it represents 3 hydrogens, it should integrate 3 times as much area. This one is the one that's 2. So let's earn back my 1 point I lost. Its integration, or its area, should only be twice as much as this one. So in some of the homework problems, they throw these little curves up right up by the peaks or above the peak, so you can say, ooh, what's the ratio? Well, this is a 1 to 2 to 3 ratio. Sometimes they'll be nice to you in the homework problems. They'll actually write a 1, a 2, and a 3 above them. That is supposed to give you a relative ratio of the quantity of hydrogens. But often it's just these integration bars. The bigger the bar, the more hydrogens it's worth. The smaller, the less hydrogen. Okay, and that's one of the cool things about Proton Nmr. Okay, now what I'm going to do is we're going to take and do a series of examples with the exact same formula, just to talk about them. And then I need to do carbon-13. So the formula we're going to use is C4H10O2. It's a very interesting formula because if you include geometric and stereoisomers, there's over 50 different compounds possible with this formula. I'm not going to give you the assignment to come up with all 50 compounds. I just want to do a couple of them. Now, when I have an NMR problem and I'm given a formula like this is empirical, the first thing I always want to do, whoops, I don't want 10. There was a typo. This was C10H48. Now there's 50 different ones. With 2 hydrogens, you lose all the different possibles, over half of them. C4H8O2, sorry, I messed that up. We'll write it correctly on the next one. Having 2 hydrogens missing has an IHT equal to 1. And when you start having IHTs that are not 0, this 1 can mean a double bond. That double bond can be anywhere, or it can be a ring, and that ring size can be any size that can fit these molecules. And so if you start to imagine all the different places you can put a double bond, or all the different ways you can make rings, and then you start to include RNS and cis and trans isomerization, you start to see that there's a lot of different compounds possible with just this one empirical formula. Okay, I'm going to do, what am I going to do? I'm going to do 4 of them. 2 of them I'm going to do side by side as a direct comparison. We're going to do it underneath here. And that is, we're going to do methyl propanoate and then right next to it, or right under it, I'm going to do ethyl acetate. Now, if you look carefully, the only difference between methylpropanoate and ethyl acetate is I moved the oxygen from here to here. Does everybody see that difference? Okay. We should be able to easily distinguish that difference on an NMR. Okay. So I'm going to label my hydrogens again. We'll label them all the same. A, B, and C. And these will be A, B, and C as well. A, B, and C. And to show you what happens just by moving one oxygen. Okay, we're going to draw two spectrums over here at the same time. We'll start at 0. Go 1, 2, 3, 4. And we'll do the same here. 1, 2, 3, 4. Okay, so I'll start with the first one. A, the methyl, has 0 neighbors. He's all by himself. That means he remains a singlet. He's touching the oxygen. That puts him at 3.1. We give him a nice large signal, and we call that A. Now I'm going to do the opposite. We're going to do conversely. This guy's A. So switching colors. Let's switch to brown. Okay, this guy, still a singlet, has no neighbors, but is he touching an oxygen? No, he's next to a carbonyl. That means he is going to be around 2.1. So here, because he has a different environment, he's at a different shift. Okay, let's move back. Let's do B now. B has 2 hydrogens. Next door is 3. So if you remember, 3 splits him 3 times. He'll be a quartet. He's not touching an oxygen, but he's next door to a carbonyl. So B will be a quartet at 2.1. Okay, switching now to this guy's B. This guy has the same thing. Yes. Whoops. Who put a 2 there? He has 3 neighbors next door. That splits him into a quartet. He's touching the oxygen. So that means he's going to be up here as a quartet. And B will be there. Okay. So then that brings us to C. C has 2 neighbors. That means these guys will be a triplet. And he's 2 away from the carbonyl, which means next door, B being 1 away from the carbonyl, he was right here. Next door to the carbonyl, he's not going to hardly be moved at all, or 2 away, so we're going to leave him below 1. We'll put a nice triplet here, and we're going to call that one C. This carbon is next door to an oxygen. That's a little bit stronger effect than the next door to the carbonyl effect, because this guy was right on the oxygen as he's here, but he still has 2 neighbors, going to be triplets, so he might be right on 1. Not much difference between the 2 different C's. Okay, but what you can tell is the position of the oxygen was determined strictly by which one of these 2 peaks was shifted. When it was next to the oxygen, the A signal moved up. When it was next to the ethyl group, the B signal was the one that was shifted. Okay. Now, let's do 2 more with the exact same formula, and then I need to move on to carbon 13. And then we'll be good. So, same formula. This time I'll write it correctly. C4H8O2. Okay. One of the structures of C4H8O2 is one that I'm going to draw it in line form, where it has a carbonyl and it has an alcohol. And I can put the alcohol anywhere I want, but today I'm going to put it right here. A lot of different possibilities. And And actually, I'm going to do 3 more. I just thought of another one I want to do. So this time we'll do a carbonyl at this end. And we'll put the alcohol at this end. And again, these are isomers, the exact same form as this one. And the last one I want to do, I need to talk about, because this one's very important, is dioxane. That's where it makes a cyclic compound with 2 oxygens in the middle. This one, so CH2, 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 and the 2 oxygens. It's a very cool compound. Okay, so let's look at all of these. And I'll save that one for last. So again, I need to do some labeling. This one, unlike the previous ones, we have hydrogens here. We have a hydrogen here. Don't forget. And then we have 3 hydrogens there. So CH3 is CH3. I'm going to just put in the CH3s because that'll help us remember and to count neighbors. These guys are all CH2s. So CH2, 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 and these are all CH2s we'll come to later. Okay. So remember the diagram I gave you of the houses and the next door effect. It'll become important when you draw these spectrums. So okay, this one I do not need too many numbers. We're going to stop at 5. Okay, so which ones do we want to do? I got to first now label A, B, C, and the OH will be D, and then we'll do the same here. A, B, C, D. Oh, this one has 3, E, and I'll do that one later. Okay, so on this one where we have it, we'll start with A. CH3, no neighbors next door, next to a carbonyl. We'll have a nice singlet, and we'll label that one A. Okay. B. B has an oxygen on it, plus it's next door to a carbonyl. Ooh, we'll have a double shift effect. I'll come to that in a minute. And neighbor-wise, OHs do not count as neighbors, but these 3 are neighbors. So he's going to be a quartet. The oxygen shift effect is here, 3.1, and next to the carbonyl, we'll probably move it up 1 more. If you remember, being next door to the carbonyl, A's were moved up to 2. These effects kind of are additive, so we'll have the oxygen effect plus the carbonyl effect. I'm going to predict B to be over 4. With 4 neighbors, B will be a teeny tiny quartet, and the reason he's tiny is he's only worth 1 hydrogen. But it'll still be a quartet because of his 3 neighbors. C has 1 neighbor. That means he's going to be a doublet. He's 1 away from the alcohol carbon, which might move him up to 1. And he's worth 3 hydrogens, so it'll be a fairly large doublet. And we'll call that C. And that leaves the OH. Remember what I said about the OH. Just find the spot and put it. You could be right, could be wrong. I won't mark it wrong if it's in the right range. So between 1 and 5, the OH can be anywhere you want. Okay. So again, I'm going to throw in integration bars really fast. Remember, B was only worth 1 hydrogen. He should have the same integration bar as D, only worth 1 hydrogen. Both A and C were worth 3 hydrogens, so they should both be whoops, I'm going to need more space. I ran out of space. We'll make this one bigger. We'll need 3 times integration. So basically a 1-to-1 to 3-to-3 ratio were the signals on this one. Okay. When we do this compound, again the same formula. I'm going to need a lot more numbers. And that's because A is an aldehyde. And if you guys remember where aldehydes were, that was up there. at 9.5. So I better draw in. I need to go to at least 10. I'm running out of room. We'll go a little bigger. Okay, 10. Alright, so I needed more numbers just because I knew A was going to be more shifted than all the others. Okay, but the neighbor effects are still the same. So A is next door to B. B has 2 hydrogens. That means A will be shifted twice. He'll be a little triplet. We'll call that one A. Okay, way up at 9.5. B is next door to the carbonyl. If you remember, that shifts 2.1. Now, how many neighbors does B have? Well, he has 2 on this side, and he has 1 on that side. We're going to make those additive, so that's 3 neighbors in total. That'll be a quartet then for B. Everybody see how that works? Okay. Now, if we look at C, okay, C is 2 away from the carbonyl, so that's really nothing, and 1 away from the alcohol. He'll probably be somewhere around 1. How many total neighbors does C have? Well, he has 2 here and 2 there. That's 4 neighbors. That means C is going to be quintet. The quintet was that 1 to 4 to 6 ratio, which looks something like that. 1 to 4 to 6 to 4 to 1. Okay, so we put C way down there as a quintet because he has 2 neighbors there and 2 neighbors there. Okay, and that leaves us D. D is on the oxygen. That puts him right here at about 3. He has 2 neighbors next door, so he'll be a triplet. That would be D. And that leaves the alcohol, and you look for an empty spot. I'm going to put my alcohol right there. I'll call that one E. Sometimes in real life spectrums, the alcohol peaks end up on top of one of these others. And so you'll have a lump that's next to a splitting pattern. And so they'll sometimes expand that or blow it up so you can see the difference. Okay, and let's really fast put in our integration curve. So again, the aldehyde hydrogen was only worth 1, same as the alcohol. All the rest of these were worth 2, so they all should be twice as tall as the alcohol. And you have your 2 to 2 to 2 to 1 to 1 ratio. Okay. Now, the reason I picked this last compound is a concept that we call the concept of symmetry or identical. If you look at these hydrogens, they are all identically the same. So these CH2s have 2 neighbors next door. This one has 2, this one has 2. They're all attached to 1 oxygen, all attached to 1 oxygen. And even though, if I asked you, how many next door neighbors do these guys have? And you might say 2. When they're identically the same, because of the plane of symmetry, they never split each other. To say that differently, identical hydrogens, even if they're next door, do not split. This is something to do with second order effects where 2 signals merge together and become a singlet. So what happens is all 8 of these hydrogens will all show up as one peak right about 3.3 as a singlet. There is no distinguishing hydrogens. And when we go to carbon 13, all the carbons are identically the same. They will not show up as any type of signal as well. So even though they have next door neighbors, they don't split each other if they're identical. And that happens in compounds where they're symmetrical, where the middle is exactly the same and they branch out. They love symmetrical compounds a lot in the homework. So I've given you now 5 examples of the exact same formula, but completely different structures with different spectrums. And as you can imagine, there's a lot more to choose from. I wanted to now go to some of my bookmark pages to show you some of the tools they give you to help. Okay, so here's a homework problem that's not focusing. Sorry about this. There it goes. Got to bring it into. Come on, come into focus. Why aren't you?
Just stop.
Just stop?
Yeah, stop. No, stop the video.
Oh, pause?
Yeah.
Okay, we're pausing video. Okay, continuing. We refocused, and I wanted to talk about these inserts. Oftentimes, and this is a typical homework problem right out of chapter 14 where we did aromatics. So you see all the aromatic curves, and you see the nice integration bar. And then what they did is, it was really hard to see the splitting patterns, so they blew it up right here. And what's really cool about this one is I can now count peaks. 1, 2, 3, 4, 5, 6, 7. Oh, this little signal will split 7 into 7 peaks. That means he must have 6 neighbors. Now, if I look over here, this peak, they blew up here so I could see it better. I can see it's a doublet. This peak is only split by 1 neighbor. Well, a 7-plet or septet next to a doublet is very typical of an isopropyl group. So I'll lay money that this compound is isopropyl stuck on a benzene ring, which is better known as cumene. And if I do my integrations now, you can sometimes use a ruler. It's often useful. And I'm going to go from 1. So that's basically 1/4 of an inch was worth 1 hydrogen. This should be worth 6 of those, so that should be 6/4 of an inch, which in layman's terms is 1.5 inches. And you'll see, yeah, the integration almost went exactly 1.5. And that's to give you a relative comparison. And that would have been the 1 hydrogen next to 6 hydrogens. This is the 2 CH3s next to that 1 CH. Now, if the benzene ring has only one thing attached to it, then the other positions on the benzene ring should be 5 hydrogens. So relatively speaking, how this was 1 to 6, this one should be 1 to 5. So if the 1/4 inch is still approximately what 1 hydrogen in, we got 4/4. Ooh, it came out almost exactly 1 to 5. So these integration curves, as I mentioned earlier, is to give you a relative quantity of hydrogens comparative to each other. And I always personally try to find the smallest one, and I think is 1 or 2, and then do a comparison to that. And we'll slide up this one here too. You see, here's another compound, except now it has nitrogen on it. It has this quartet that was blown up next to a doublet. And now I'm going to look at these integration curves. So this one looks like 1. This one looks like 2. This one looks like 3. And here's another clue. They gave me a formula. 11 hydrogens. 1, 2, 3. That's 6. This one better be worth 5. And it actually is approximately 5 hydrogen. So again, 5 hydrogens in the benzene region means we have a monosubstituted benzene. The 2 hydrogens here, that's a broad singlet. That's probably an NH2. In fact, you can take my word on it. It's an NH2, the lovely broad singlet. This one was a quartet and a doublet. That must be a single hydrogen next to 3. And the NH2 is probably on that hydrogen. This guy was double shifted. He must be touching the benzene ring plus touching the nitrogen. That gives him a double shift. So the nitrogen shift is here, touching the benzene, brought him up to 4, which is kind of cool. Okay, so anyway, as you can see, these integration curves and these inserts are pretty useful. I'm going to now flip over to a different chapter that was in aromatics. And I'm going to show you this spectrum right here before we go down to carbon 13. Okay. Where's the one that had the impurity? This one has a singlet, some aromatics, and some integration curves. And these two, if they blew up from here to here, is actually, you can see now, is two triplets. They're kind of bent weird. And that bending weird is what we call the second order effect. That's when the two signals get close to each other, they start to merge. The inside goes up and the outside goes down. But they're two different signals, and it looks like they're each worth about 2 hydrogens. So we got 2 hydrogens, and 3 hydrogens. That's 7 hydrogens. We only have 12, so that must be 5. Again, our integration curves are there. Okay, so the last spectroscopy we need to talk about is carbon-13. I'm going to redraw this one, but I like this one because it's very simple. It's a nice example. Carbon-13 doesn't have the normal splitting patterns unless you uncouple the decoupler that took away the hydrogen split. Let me say that differently. Carbon-13 is not the most abundant isotope of carbon. It's a little less than 2% of all the carbons. Most of the carbons on our planet are carbon-12. And so carbon-12 does not have a magnetic signature, unlike carbon-13. And so what happens is a carbon-13 next door to a carbon-13 will not split each other because the probability is only 2% of 2%. And if you guys are good at your math, that's 0.04% chance of even being next door to each other. It's a very slim chance. So the only magnets that are actually touching or affecting a carbon-13 would be the hydrogens that are actually on the carbon. And so what they do is they decouple it. It's called proton decoupled, or DEPT for short. A DEPT carbon-13 doesn't allow the hydrogens to split the carbon. The carbons remain singlets. And in a DEPT structure, all we look for are the shifting patterns. Also, because the carbon-13 is not the most abundant form of carbon, the relative heights are not proportional to the number of carbons necessarily. Oftentimes, the relative heights are proportional to the number of hydrogens attached. For example, I know in this case that there are the same amount of CHs as CH2s in this particular compound. I'll just tell you right now, this compound is diisobutyl ketone is its common name. We'll go back to that in a second. But the number of CHs and CHs are the same, but generally when you have more hydrogens, you tend to have a slightly higher peak. And when you have 0 hydrogens, like carbonyls, and this is a carbonyl carbon, you tend to be tiny peaks that are practically invisible. You guys see how tiny that is? That's not always the case, but that's just a generality. And usually methyl groups have the biggest peaks. But this peak is doubly big, and that's because there's twice as many methyls as there are the other guys in the diisobutyl ketone. Okay, so the main thing in carbon-13 NMR is the shift. If they add the hydrogen count, that's a bonus. They often won't do that, but sometimes they do. Let me see if I had another one handy. Okay, so I'm going to now give you the shifting rules for carbon-13, and we will more or less call it good for today. So, the carbon-13, and we're going to decouple the proton. So this is the decoupled proton, or DEPT experiment. Now, I want to go back and refer as a reference the general shifts we had of the carbon, of the proton shifts, and do a side-by-side comparison. They are close, but they're not identical. Okay, so in the carbon-13, it still starts off with 0, but if you were to match up numbers with the proton NMR, 3 is equivalent to about 50. And then we got 100. After that, the equivalencies go away. So 100, 150, and 200. Okay. So what happens in the first 50s region, the signals you have for hydrogens on carbon all remain about the same. So the lowest ones, let's break this up, 40, 30, 20, 10. Boring hydrocarbons, primary, secondary, and tertiary, they all show up here. Primary, secondary, tertiary. Primary, secondary, tertiary. Right around 10 is the normal shift for primary, secondary, tertiary. The next door effect that we had at 2, when you're next door to a carbonyl or to an aromatic, those usually show up in the 30s. 20 is a 40 region, anywhere in here. So we'll put those in here. So the next door effect, that's a carbon next door to a carbonyl, or a carbon next door to an aromatic, usually shows up between 25 and 40. Okay, the electronegative atoms usually show up right between 50 and 60. That's the effect of electronegative atom. The nitrogen effect is just below 50, usually in the 40s. And so a lot of students say, oh, there's almost a direct parallel. And there is in the first region. The shifting here is almost identical to the shifting here. What changes is everything else. Okay, and that is the pi bonds. Okay, the pi bonds do not follow the same as a proton NMR, and so I always like to start at 125. In the 125, you have almost all your carbon-carbon double bonds. Okay, in the aromatic regions, the carbon-carbon double bonds that are aromatic and the ones that are not, they're all at the same spot. But they have the similar shifting effect. If you have electron donating groups, ortho and para, to a carbon, it goes this way. Conversely, if it has an electron withdrawing group, ortho or para, the carbon shifts proportional. So in the hydrogen shiftings that were ortho and para, the carbon shift the same. If it's right on the carbon, for example, if an oxygen was sitting right on a carbon, the double bond and the electronegative atom effect adds together, and so this is usually an aromatic with an oxygen or a nitrogen or something. You get the effects, and so you'll go 150s all the way up to 160s for the carbon of that double bond. And again, this can happen also if you have a carbon with a double bond on a chain, you stick an oxygen on it through an ether. So the oxygen effect will be added to the double bond effect, and you end up at 150s to 160s. You get a nice additive effect. Okay, the 200 region is typical of all the carbonyls. Okay, generally speaking, if you're down in the 170s, 180s, that's acids and esters. There's not an absolute rule on this. And if you're around 200 or above, that's generally aldehydes and ketones. Again, it's not absolute, but generally a carbonyl is here. Now, if you remember that spectrum I showed you earlier, that little tiny peak for the carbonyl right there, it was right around 200. It was actually at 212. If you go back in the video, you'll actually see it was at 212. That was another clue. It told me I had a ketone because it was above the 200 line. And it was a tiny peak. Okay, that leaves the triple bonds. The triple bonds usually are between 75 and 100. Triple bonded carbons. Okay. And now I want to show you one more thing that you never want to look at. We're going to go back to the spectrum I showed you earlier. So, again, I told you the carbonyl was at around 210, 212. Classic ketone. This is definitely a ketone. It's this guy here. Always around 77 is what's called the chloroform carbon. Deuterated chloroform is the solvent. And it's always a triplet because the three chlorines cause it to do a cool little splitting pattern. It has to do with the different isotopes of chlorine. But one thing you never want to do is include this as part of your compound. This is a solvent. And in other NMR problems, they might have this little word, impurity. That means this peak is not part of the compound. The compound does not include that peak. So deuterated chloroform and impurities, when they label them as such, please don't include them. So I wanted to do two more carbon 13s. And again, these come from your book. Sorry. I'm losing my light when I do this. Okay, we'll do what we can. These two are interesting because, let's see if I can put them at the same time. This is from a later chapter, chapter 20. I'm not going to give you the exact ones in case you want to go home and work on it, but I wanted to point out, see the chloroform peak? That's not part of the compound, and the same one here. Basically, these are two isomers with the exact same formula, but the patterns change. There's a different splitting shift here. This one is the aromatic region, just to let you know. You see that we're around 125, and some of the carbons is shifted up. This shifted up to a higher number or to a lower number. That gives me some clues as to which is which. The one that's right at 125, he's the one in the meta position. He hasn't moved. This one, same formula, but a different structure, different shifting pattern. More clues. And again, we have a different set of shifts there. So these are fun problems to try to work through. I'm not going to do them for you, but I just want to show you that the only thing that we're really checking is the shifting patterns here. So these guys are alkenes. And by the way, I'll give you one hint. See this shift at 45? This carbon must be touching the nitrogen. And this shift at 148, that carbon's touching the nitrogen. So I now know my nitrogen is between that carbon and that carbon. On this one, don't know that. It looks like I have a next door effect. Something completely different is happening. So this carbon is not touching a nitrogen because he does not have the same shift. But this carbon is still touching a nitrogen. There. I gave you some clues if you do this one as a homework problem. But the shifts alone told me, nope, not touching nitrogen. Yep, definitely touching the nitrogen. Okay, and that's it for carbon 13. Now your job is to practice looking at problems, and then we have some where we give you a structure and we want you to try to draw. And when you're doing a carbon 13, you're just trying to approximate the relative position of peak A, peak B, peak C, D, E, and F for the different carbons. Okay? And that concludes this discussion of NMR.